So just a quick recap on what we covered on Tuesday, and then we will continue and look at electron cyclotron emission. So first of all, we had a look at the radiation transport equation. And we wrote this radiation transport equation in terms of the intensity of light, spectral radiance to be correct, coming out of plasma, and how it changes along the path through the plasma. So we've got a little plasma here, we've got some path going through it that we parameterized by S. And the change in this spectral radiance is equal to a quantity J, the emissivity, minus alpha times the spectral radiance. Alpha is the opacity here. And it's convenient to rewrite this equation in terms of a dimensionless parameter tau by dividing through by alpha, and then we get this compact form of the equation, di d tau is equal to j upon alpha minus I. And what we've done is we've defined this parameter tau as being equal to the integral of alpha ds here. And again, this is an indefinite integral. It's only when we start putting limits on this that we know whereabouts we're integrating from and integrating to. And the other thing to say is that this equation is true for all frequencies. And maybe we'll write these in terms of cyclic frequency or rads per second or wavelength or energy, whatever it is, just some way that we're measuring the difference in the spectrum here. And this equation then can be solved separately for all the different frequencies in your system. In our assumption here, we're not allowing the frequencies to interact in any way. There's no second harmonic generation. There's no absorption and fluorescence and things like that. And this tau parameter is a nice dimensionless parameter. So of course, the first thing we want to do is work out what it means for that dimensionless parameter to be small and what it means for that dimensionless parameter to be large. In the case where the parameter is small, we find a plasma which we call optically thin, which means that radiation streams through it without being absorbed, and there's minimal emission in this. In the opposite case, where tau is greater than 1, our plasma is thick, and incident radiation is strongly absorbed, and the plasma is also strongly emitting. And in fact, we found out that in this thick case, our plasma is going to be so strongly absorbing that it's going to approximate a black body. And a black body has a spectral radiance that looks like mu squared upon c squared times the temperature. So it doesn't depend on any particular properties of your material. It just depends on its temperature. This is the Rayleigh-Jeans approximation. The full black body is more complicated, but most of the time we can use this Rayleigh-Jeans approximation. And the neat thing about that is we found that there was a correspondence between this equation here in the optically thick limit and the black body equation, which is Kirchhoff's law. And Kirchhoff's law lets us set the emissivity over the opacity equal to the frequency squared over the speed of light squared times the temperature. And this effectively tells us that the emissivity and the opacity are linked together. And so if we calculated one, we automatically have a calculation of the other. And simultaneously, if we have a region with high emission at some frequency, that's also a region with high absorption as well. So these two quantities are linked. Okay, and then we talked about how to actually calculate J and therefore alpha, so that we can use this ray transport equation to see how plasma allow electromagnetic radiation to propagate through it. And we did a sort of pictorial representation, and Tucker sent around a very good sort of web demo that you can play with to play with that pictorial representation of why accelerating charges radiate. And we also wrote down a very long equation and then immediately dropped the near field term, but the remaining term, the far field electromagnetic radiation from moving charge, was equal to something with a bunch of constants, and a few new variables related to where we are with respect to the particle. But the key part of it was that we started getting these cross products here that have within them some properties of the particle itself, namely its velocity crossed with its acceleration. And so it's clear that in order to estimate the radiation from a moving charge, we're going to have to know these two properties. And so the recipe that we're going to follow is we're going to firstly calculate V and V dot, and we're going to do that with the equation of motion. And then secondly, that would give us the radiation from just a single charge. We then need to integrate this over the distribution function f of v, v3v, to get out the emission from all of the charges in the plasma together. And that is going to give us the emissivity at a single point, and then of course, because they're linked, also the opacity. So this is what we're going after. Any questions on that before we move on to an example of this? Yes.
Can you explain again why we dropped the near field in the electrical?
Yeah, so the near field term, which I haven't written down here, the near field term goes as 1 upon r squared, whereas the far field term goes as 1 upon r. So when you calculate S is equal to E cross B, I'm going to write the mu naught, so proportionality. The magnetic field is going to have the same radial dependence, the same drop-off in distance as the electric field. And so the Poynting vector is going to go as 1 upon r to the 4. And that means that if you go far enough away from the particle, that electric field and therefore the radiation from it is going to drop off faster than r squared. And so you're not going to see it from any reasonable distance away. And in fact, the distance you need to be away is a few wavelengths of the radiation. And so that's usually quite short. So we don't have to worry about this. Effectively, what your electric field looks like, and I had a little chat with Sean about this after the class, so hopefully I remember it. The electric field that you as an observer would see at some function of distance has a 1 over r component, which is the far field, a much more steeply dropping 1 over r to the 4 component, which is the near field. And so you don't, as an observer, get to see the difference between these two. They look the same. What you'll end up seeing is just some field that looks like this, but the far field, the near field component won't show up at any sensible distance away from the plasma. So we do not need to worry about it in plasma physics, as far as I know, but maybe there is some special case you do think about it. But we're going to drop it in these lectures. Yeah, Sean.
It makes sense that we don't need the near field for trying to observe the radiation that's emitted, but if you're trying to couple the emitted radiation back to the plasma for the absorption, shouldn't the near field contribute to that? Because you do have particles that are, near the emitting particle.
Okay, so for the benefit of people online, the question is, doesn't the near field perturb the plasma? I don't know. I could hand wave and say something about the lengths. The plasma is very good at shielding out electric fields, right? And so maybe it will depend on the wavelength of your radiation compared to the Debye length of that. But I'm just spitballing here. I don't know the answer to that. Yeah. Thank you. You're going to love my next. I went to talk to Paul Benoli, and I'm like, hey, Paul, is this right? And he's like, yeah, that sounds right. So you're going to love my next approximation a little bit. So, okay. Any other questions? Anything online? Okay, let's keep going. So we're going to be looking at electron cyclotron emission. or ECE. This is a key diagnostic in magnetically confined plasmas. This is a very, very important diagnostic, which is why we're going to spend a significant amount of time on it. This diagnostic works on the basis that we have magnetic field lines inside our plasma, and we have particles, electrons, which are spiraling around those magnetic field lines. There is also ion cyclotron emission as well, which we are not going to cover here. I believe that's because it has a much harder time propagating out of the plasma, and we'll discuss a little bit about that later on. But at the moment, we're just focusing on the electrons here. And so what we want to do, as we said before, is write down an equation of motion. And that equation of motion is going to be simply that the time rate of change of the momentum of our electron is going to be equal to the force on our electron. So this is EV cross B here. We're assuming that there, in this formula, that there are no electric fields. So we're just dealing with the particles gyrating on the magnetic field. You've seen this before, you've solved this before. The one thing that Hutchinson puts inside here that we didn't have previously is this factor gamma. So this is the relativistic gamma here, and that is 1 minus b squared upon c squared to the minus a half. Gamma is always greater than 1. And this is a factor that effectively, in this case, if you want to think about it as increasing the rest mass of our particle, and this is because our particles tend to be moving in like a MCF plasma, where the electrons are at 10 keV or 20 keV. That's a significant fraction of their rest mass, and so there will be some relativistic effects on top of this. So in this case here, we know that this, because we've solved this equation before, we know that this electron is going to oscillate. I guess I can be precise, I can say it's going to gyrate at a frequency omega c, the cyclotron frequency. And this is just ever so slightly different from our normal gyro frequency, because it's different by a factor of gamma here. So the gamma changes a little bit. And so this is just E0 over electron mass times by gamma. Again, if you just keep the gamma sticking with the electron mass, you won't go too badly inside this. Because the electron is gyrating at this frequency, it is reasonable to believe that there is an electric field it generates, which is also gyrating at that frequency. So this means we expect to have radiation this frequency as well. And that's true, we do have radiation at that frequency. But the thing I've been struggling to find an intuitive explanation for, I went to go talk to Dr. Benoli about this just before this class, is that we don't just get radiation at this frequency. When you go into the mathematics of it, you find out that you get radiation at integer multiples of that, at harmonics of that. So we also have this factor of m here, where m is some natural number. Now, mathematically, I can tell you where this comes from. It comes from, for example, Hutchinson's equation 5.2.7. What this is there's an exponential of some horrific quantity, and Hutchinson and everyone else says, well, fortunately, there's a really great trigonometric identity that converts the exponential of this horrific quantity into a sum over an infinite number of Bessel functions. And those Bessel functions are all oscillating at harmonics here, and so therefore you've got all these harmonics, right? So mathematically, it all makes sense. No one is upset about that. The trouble is that it doesn't make any physical sense, right? Like, as far as I can tell, like, there's no reason why electrons should have to care about Bessel functions any more than I do, right? So something is going on physically, and so I went to go talk to Paul and ask about it, and the thing we came up with is whenever you have harmonics in a system, in some sort of simple physical system, it's usually due to some non-linearity, right? So we need a non-linearity in our system where the system acts back on itself in order to produce it. And what our best guess is that the electric field that you produce at the fundamental frequency here, omega c, is going to go back and couple back into the electron equation of motion. So it's effectively the electron is going to be forcing itself slightly out of phase, and that is going to give rise to these other harmonics here. So this is sort of a way of trying to make the system non-linear, because of course this electric field depends on V dot and V, and that's the thing we're solving for over here. So we think that it's a non-linearity. So we think that these harmonics are due to non-linearity. We looked at sticks, we looked at Chen, we looked at Croydon triple piece. We couldn't find anyone who was willing to tell us what the answer is. So if anyone has any insight into why it's the case, and if it's better than just waving my hands and saying non-linearity, then please go for it. But the alternative is you just have to treat this as a mathematical exercise and churn for the algebra. And I assure you, if you go and have a look at this, you'll see that it really is an awful lot of algebra. So I'm trying to keep the mathematics out of this as much as possible. But if you go and do this properly, you find out, and this is equation 5.2.16, you're going to get a set of peaks in your emission, and those peaks are going to be at frequencies omega m, which are equal to m omega c, and they're actually going to be modified due to relativity, and they're going to be 1 minus beta squared to the half. I'm going to explain what beta is in a moment. 1 minus beta parallel plus theta. I'm going to explain all of these terms in a moment here. So we've still got this m inside here. It's just that there's also m is some natural number. It's just that we also have some modification due to relativistic effects here. So what are these betas? Some of you have come across these before. This is absolutely not the plasma beta, right? It has nothing to do with the plasma beta. This beta is defined as V upon C, so it's the ratio of the particle's velocity to the speed of light. And we also have beta parallel, which is equal to V parallel upon C. That parallel is with respect to the magnetic field, C0 here. And I don't think it comes up, but you can also define beta perpendicular if you want to as well. Okay, there's something else I wanted to mention all this. What? Oh, that was the one. Thank you. Yes, I forgot to draw the diagram early on. So theta in this case is the same theta that we had when we were talking about X mode and O mode and all that sort of stuff. It's the angle between the observer and the magnetic field here. So this is a term that is largest when you're looking along the electron's trajectory towards you, and smallest when you're looking perpendicular. And so you can see straight away, this is a signed quantity. It's going to end up looking a little bit like a Doppler shift. So that is the Doppler shift that you were expecting to see. But it's, you know, relativistic Doppler shift here. Okay. So for a single particle, just some electron moving on a magnetic field, we would have an emissivity that looked like a series of these peaks, okay? And these are delta functions in the theory. So you just have these very sharp emission lines, and they're evenly spaced.
The height's the same.
Their heights are not the same. If you want to get their heights, you have to go look at all those nasty Bessel functions, right? Which I'm hiding from you. But if you want their heights, it's the argument of the nth Bessel function. And the thing that goes into the Bessel function is some complicated factor of all these other things here. So again, I'm not going to explain it, but they do not have to have the same heights, which are why I've drawn them a little bit like this. And if that particle is moving particularly fast, then all of these will be shifted in one way. And if you're looking at it from a certain angle, will be shifted another way. But they'll all be shifted in the same way, because this is just for a single particle. Okay, any questions on that before we find out what happens when we have more than one electron? First thought. Okay. So the next thing we do is we look at many particles, many electrons. And for this, it's useful to split our three-dimensional distribution function f of v, the vector, v3v, into a distribution function in beta parallel and beta perpendicular, v3v, like this. So this is looking at particles which are streaming along the magnetic, well, this is looking at the component of velocity along the magnetic field and the component of velocity perpendicular to the magnetic field. And that's because this problem is symmetric. It doesn't matter how I rotate my axes around the magnetic field. The velocity overall is going to be the same. So I don't have to actually deal with three dimensions here. I've just turned it into a two-dimensional thing. And if you do this integration, you'll find that your betas are different from different particles, right? Remember your Maxwellian. If I just take a one-dimensional slice through it, has lots of different velocities available. And so that means some particles are going to be going with a velocity which changes the sign of this to be bigger than one, and some part of this denominator to be bigger than one, some to make it smaller than one. So we can see that we're going to have broadening of these peaks, and this is the Doppler broadening that we expect. So let's just draw a single peak. It was a delta function at m omega c. Doesn't matter which harmonic is for our purposes. This delta function is now going to be broadened out. So I think the delta function was always rather unscientific, unphysical, and so it's going to be broadened out by these natural broadening processes. And there's two of them, right? There's this top process and the bottom process here. I'll just write them out again down here. So we have a factor of 1 minus beta squared to the half over 1 minus beta parallel cosine theta. So let's start with the numerator, the denominator here, the term on the bottom. For some symmetric Maxwellian-like distribution function, what does this term do to this line? How does it broaden it? Is it symmetric, asymmetric? Imagine we're looking at a fixed angle, because we don't have eyes all the way around the tokamak, so you can just fix theta to be some angle. Pick an angle where cos theta isn't 0, otherwise it gets very boring. What will this term 1 minus beta parallel do? Yeah.
It'll broaden it symmetrically.
It'll broaden it symmetrically, right? This is going to look like, say I look along the field line, cos theta equals 1, theta equals 0. This is going to be 1 plus or minus v upon c. And the plus or minus there is saying for every particle going along the field line towards me, there's another particle going away the other side. And this is also going to be very small because the particles we're not dealing with like actually ultra-relativistic particles here. And so this is going to look like sort of 1 plus or minus delta. And that means that it's going to broaden this peak symmetrically. What about this term at the top here? So you can call this the Doppler term. What does this term on the top do? Anyone online? Is it always bigger than 1, always less than 1, sometimes bigger than 1, sometimes less than 1? Yes.
It's always going to be less than 1 since beta squared is always positive.
So this is always less than 1, because as you say, beta squared is always positive. So it doesn't care about the sign of v, so it's going to be asymmetric here. So this is the relativistic mass term. And that will broaden the peak further, but it'll only broaden it in one direction like that. So your peaks end up looking like this. If you want to know which of these two terms is larger, then you're asking the question, when is beta parallel cosine theta greater than beta squared? That's the case when cosine theta is greater than ut upon c, the thermal velocity of the electrons. And that's the case for theta less than, but almost up to pi upon 2. So for almost all angles, this Doppler term dominates.
You're beta grade. Is it beta less than or? is beta
Oh.
greater?
Yes, you're right, sorry, thank you. But almost all theta, apart from theta exactly equal to pi upon 2, the Doppler term then. So you'd see mostly symmetric lines with some small asymmetric shift, apart from if you're exactly pi upon 2, which is a place you're often at when you're looking inside a tokamak, right? So this could happen quite a lot, in which case you're going to see a line that is very asymmetric indeed. Okay. Questions on this? Yes.
What is the J in the single particle graph?
That is the emissivity, the thing we're trying to calculate. Hutchinson writes it in a sort of differential form, which is nice for keeping track of units. I'm just going to call it J. And you know, sometimes there's some steradians and stuff flying around that you have to deal with, but roughly this corresponds to your intuition of brightness, right? This is how bright the plasma is with this magnetic field and this velocity for this single particle. And then of course, all of these lines will be broadened by these terms. Okay, yeah.
I was a little confused with the picture with the, where we do the asymmetric peak,
Yes.
right? Because the orange equation on the right is saying, right, that slower particles will have a less, that like a less reduced peak. Is that what's, I guess I was just trying to think about the way that you drew
The relativistic mass correction or
Yeah.
the,
yeah,
well, actually, this is due to fast particles.
okay, yeah.
They're so fast, they're so heavy, their gyro frequency has gone down.
Oh, okay, yeah.
Yeah, good question. Yeah. Yeah, you're right. That's maybe counterintuitive because actually for the Doppler shift, the particles down here are the fast ones. Oh, it's true in both cases. Yeah, it's the fast ones in both cases. Yeah, these ones up here are the fastest particles. Any questions online? Okay. So we use this in practice by having a very good idea of what the magnetic field profile is inside our plasma. And a good example of a plasma where we have a very good idea of the magnetic field profile is a tokamak, or maybe something like a stellarator, something that's very low beta. So I'll show you what we do in that situation. So this tends to be used in magnetic confinement fusion with beta, that's the thermal pressure over the magnetic pressure, I don't make the rules, is much less than 1, nothing to do with the other beta, right? And this condition effectively means that no matter what your plasma is doing, your magnetic field is pretty much the same. So you know your magnetic field profile. And a good example of this would be inside something like a tokamak, where we have an axis of symmetry here, and I have some cross-section of my tokamak like this, and maybe the magnetic field in this tokamak is going to be dropping off as 1 upon R. That just comes from Ampere's law, the fact that you have current flowing up through the magnets in the middle. It can hardly be anything other than 1 upon R, and that's true. And so the interesting thing here is that different regions of the plasma have different magnetic fields. Maybe some of you can see where this is going. I'm making sure. So we can call these, for example, R3, R1, R2, make no sense. R1, 3 different radii here. And what we're going to do is we're going to observe this plasma with some microwave antenna, some sort of horn that's going to collect the electron cyclotron emission, which is in the sort of gigahertz range here. And that electron cyclotron emission is going to stream out in every direction. But one of the directions it's going to stream out into is our horn, so hopefully we can catch it. And then what we'll do with the signal that comes into this is we will split it a load of different times. I'm just going to draw n times here into n separate channels. We'll have a little bandpass filter on each of these, which selects out for different frequencies. This is bandpass. And then each of these will go onto some detector. And that detector will measure the power as a function of time contained within this frequency band here. And so this is effectively a time-resolved spectrometer kind of system. Okay. Why is this helpful? It's because, as we said before, B of R is well known. We think of the intensity that's detected on our detector over here. We're going to have some emission that's coming from R1. R1 has the highest magnetic field, therefore it has the highest frequencies. So its first emission is going to be, for example, at this frequency here, which is omega 1, like that. This is the frequency corresponding to position R1, and it's the first harmonic of it. In the same way, R2 corresponds to the middle of the plasma, the magnetic field is lower, the frequency is lower, omega 2, and R3 corresponds to the lowest magnetic field. There's no good reason for these to be the same in general, so I should just plot things around a little bit so it's clear that they don't have to be identical. But of course, as well as that, you're also going to get the harmonics, right? You're going to get a harmonic, and this is why I should have drawn these much closer together, but it would have made it much less clear, at 2 omega 3 and at 2 omega 2 and at 2 omega 1. And then, of course, at the third harmonic as well, now you can see, oh dear, these are beginning to overlap. This is getting a little bit tricky. So like maybe I shouldn't have done it like this. But they will, eventually they will overlap, right? It's the high enough harmonics, you're going to have different harmonics all interacting with each other. So these are the third harmonics up here. But if you focus just down in this region, for example, every frequency corresponds to a specific magnetic field, which corresponds to a specific radial location. So if you're seeing emission at this frequency, you know that that emission is coming from this bit of the plasma. So this is extremely powerful because you have, as well as the spectral resolution and time resolution, you now have spatial resolution. Okay. Questions on that? Yes. Yes, question online.
Hi there, Professor. So the spatial, you can get spatial resolution because of the decreasing R field, but is there not going to be any overlap with the earlier free harmonics and those? Like, couldn't you be close to W1? Is there no overlap?
Depending on where your tokamak sits out here, that gives you the gradient in magnetic field, and that gradient in magnetic field is going to determine the spread of frequencies that you have that you're observing from. If your frequencies are closer together, because for example your tokamak is further out in the 1/R field, it's a large aspect ratio tokamak. If those frequencies are closer together, you'll simply have to have a better spectrometer. there of course comes a point where all of the broadening that we talked about before is going to screw you over a little bit, and so that's going to fundamentally limit the spatial resolution you have. But broadly, you can sort of take the signal and maybe deconvolve it and say, I've got some spatial resolution here. Yeah. Really, your spatial resolution is also going to be limited by the number of these detectors that you can field. So like people will do like a 12-channel system, and then they'll effectively be able to resolve 12 different spatial locations across the plasma.
And the radiation field.
You're breaking up quite badly. I don't know if it's your microphone or what, but I can't really hear you very well.
Can you hear me now?
Slightly better. Yeah, go for it.
The detectors, these emissions, they're not happening isotropically, are they? Are they happening all over the tokamak, or
they're happening in every direction? They're not happening isotropically, and we haven't derived the pattern that they make, and it's in Hutchinson as well. And you haven't asked about the polarization yet, and they've got different polarizations too. So it's definitely not isotropic, but you should definitely imagine that these are going out in lots of different directions. And if you're one of these sorts of people who likes putting things on the high field side of your tokamak, then you could also measure this just as well from that side as well.
so you can put the detectors anywhere in the tokamak?
You can put the detectors anywhere. We tend to, yes, you can put the detectors anywhere. Obviously, this line of sight works particularly well because you're looking along the gradient in magnetic field. If you looked from above, it's a little bit more complicated, but there was a very good paper just published on TCV, the tokamak and EPFL, where they had vertical electron cyclotron emission. Apparently it helps with some issues as well. So just saying, you can put it anywhere. It would definitely make more sense to put it in the direction or against the direction of the magnetic field gradient, because you have this advantage that all the different frequencies then very clearly correspond to different places in the plasma.
Mid-plane.
Yes, I think so. Okay, do you have a question?
Yeah, I was wondering for the higher harmonics, you have the intensity increasing. Would the intensity of the higher harmonics be larger?
So I haven't really talked too much about what the intensity of the harmonics is, and you know there are formulas to work it out. I think in general they drop off, but we're about to talk about opacity effects on these lines. And so what actually happens is the lower harmonics are absorbed more and the higher harmonics aren't. And so at least I think Hutchinson has a figure in his textbook where like the second harmonics are the strongest and the third are actually stronger than the first and things like that. So it's complicated because there's a lot of factors at play in terms of what the final intensity is. Yeah, so here I'm just drawing them as different heights to show that they don't have to all be the same. But I don't mean anything by the specific heights that I chose for anything. Yeah. Sure.
On tokamak, people tend to neglect the colloidal field effect on the total magnetic field.
Yeah, so the question is, do you neglect the colloidal field? You do neglect it, of course. You don't really neglect it. You would take it into account. But in this simple sketch here, I don't need to put the colloidal magnetic field in. But you can imagine that if you did know what the colloidal field was, because you've got all your wonderful magnetics diagnostics, and you can do a magnetic field reconstruction, then you know what the magnetic field is at every point in your tokamak, and then you know what the frequency is, and so then you can back this back out again. So it is possible to have colloidal field and still do this technique. It's just the sketch I'm giving you here doesn't include it.
Then is it more complicated to get the theta because it's now the magnetic field is not just straight around the torus, it has some.
Well, you're still going to be, even if you've got a twisted magnetic field line, if you're looking from the outside in, it's still going to be at 90 degrees. It's just that it's going to be 90 degrees like that, not 90 degrees like this. Because your magnetic field might be tilted up or down, so it's still 90 degrees. If you start looking at another angle, not at 90 degrees, then of course you have to think about the geometry a lot more carefully.
Okay.
So if you're looking from, yeah. If you're looking tangentially, right? If you're doing tangential viewing of EC electron cyclotron, like trying to look along the field lines, then the colloidal field will make a bigger difference. Here it doesn't make a huge difference.
Thank you.
Cool, lots of questions. Okay, we'll go with Grant.
I'm just a little confused on the spatial resolution. So is the idea like we know the magnetic field so we can back out where the emission came from? Is that
Yes.
so? But that also relies on us knowing the velocity of the electrons to know their rest mass, or not the rest mass, their relativistic mass, right?
What you're saying is these peaks could be sufficiently broadened by these mechanisms that they overlap, right? And of course, like effectively, they will always overlap because I've just drawn 3 spatial locations, but there's an infinite number of spatial locations. And so you're absolutely right. That broadening sets a limit on your frequency resolution. You effectively convolved your signal with that asymmetric peak. And because you've set a limit on the frequency resolution, it sets a limit on how well you can resolve different magnetic field regions. And because of that, it sets a limit on how well you can resolve different spatial regions.
Sure, but like even just for a single particle, so there wouldn't be the
Yeah.
broadening effect. Like if I gave you a set of peaks
Yes.
and a magnetic field profile, would you be able to figure out where those peaks came from? Or would you also need to know what energy electron was this, like the mass was different to figure out?
I think this broadening is very small, and so this is not a huge change to your signal.
Mhm.
And then to me, it seems like a deconvolution problem,
Okay,
which like they're hard, but not impossible to deconvolve signals.
sure. Okay,
So-
maybe I'm overcomplicating it then.
I think you're thinking about like reasonable complications, but not ones that are the biggest problem with this diagnostic.
Okay.
We're about to go on to the fact that most of these lines are optically thick, and so you don't see them anyway.
Fantastic.
So yeah, but okay, other questions? Yeah.
Just what's the wavelength and frequency of these?
Oh, like what would be a typical frame?
Yeah, like is there any
Like-
risk of picking up other?
It's like 100 gigahertz or so. Okay. It depends strongly on the magnetic field. So in something like alpha C model spark, it will be much higher than it is on other devices.
There's not really, if you get some other type of radiation that kind of falls in the same spectrum, then.
Well, we will actually talk about that. Yes, when we talk about the accessibility condition, this frequency may be close to other natural frequencies in the plasma, and that may modify what we can observe. So good question. Yeah. Okay. Any other questions online or in the room? Okay, let's keep going. Okay. So, because you know the emissivity, or you can know the emissivity, hopefully you believe me that it is possible to calculate with lots of algebra the emissivity. We can also calculate alpha. And that means that you can ask yourself, what is the optical depth of one of these waves propagating through this plasma? You can solve tau is equal to alpha ds. And what you will find if you do that is that for the lowest harmonics, n equals 1, n equals 2, often, but not always, that tau is much greater than 1. So for these lower frequency harmonics, you are optically thick. Now, that's bad because you can no longer use sort of detailed structure inside these in order to work out clever things about your plasma. But it's actually incredibly useful because what we find in practice is that the intensity at these different frequencies is now just going to be the black body intensity, right? So the intensity I of nu is just equal to nu squared upon c squared times t. You'll notice I continuously switch between omega and nu, and I hope you realize that omega is just 2 pi nu, and I'm not too confused by this. Hutchinson uses nu because most diagnostics work in hertz, or at least we think about things in hertz when we're digitizing them rather than omega. But to be honest, I think that you should be comfortable enough just switching between these unit systems. Okay, so the neat thing about this is that you will then have, for this region of the spectrum, a signal that maybe looks like this. And again, this is frequency here and intensity here. And that means that at each frequency, what colors did I use? Actually, I will draw it like that. This is just the black body curve. I've actually gone and done the full thing, not just the nu squared. Do I want to say that? No, I don't want to say that. Ignore that. That's not this curve. you'll get a spectrum that looks like this. And that means for every frequency, you can measure the intensity. And so therefore, for every frequency, you know the black body temperature that corresponds to. So we have omega. This frequency codes for a very specific magnetic field, which codes for a very specific part of the plasma. And this intensity divided by nu squared times by c squared codes for a very specific temperature. And so from this, we get out temperature as a function of radius. So we can convert this spectrum into a plot of temperature inside our tokamak. So again, we are measuring in this toy example at these three frequencies like this. So we can, for example, get out the peak temperature profile. So this is extremely powerful. If we look at just the optically thick lines down at low frequencies, the intensity of those optically thick lines depends only on the plasma temperature and not on any other complicated physics. And because of that, because we have this very strong mapping from frequency, magnetic field to position, we can also take the intensity, map it to temperature, and we can get out the temperature as a function of position. So this is why ECE is so incredibly important, because of course, as I said before, it's also time resolved. You get temperature as a function of R and time. And in tokamaks, because of the existence of flux surfaces, once you measure the temperature sort of along a line, you also know the temperature along all the flux surfaces. So from your magnetic reconstruction, you've effectively got the temperature everywhere inside your plasma. Okay, this is a little bit hard to get your head around, so I'll pause there, let you think, and ask any questions.
If this is such a great property, why does constant scattering exist? What's the issue here? Why doesn't this work?
Well, constant scattering can be used in many more plasmas than electron cyclotron. So even in the non-existence of tokamaks, we would still embed Thomson scattering. Why does Thomson scattering exist? Why is Thomson scattering used in tokamaks? Well, this requires plasmas of sufficient temperature to make high enough frequencies to be detected, so it will not work in the edge. And edge Thomson scattering is a big importance tokamak diagnostic. This Thomson scattering is defined along a chord by your laser beam, and so you can get truly local measurements of temperature, whereas this diagnostic is kind of like a little bit more global. And we'll talk in a moment about fluctuations and the fact that this default diagnostic is not good at seeing small temperature fluctuations. I feel like that's enough. There are probably other good reasons. Oh, we'll talk about accessibility in a moment. So the fact that, in fact, sometimes it's very hard to do electron cyclotron emission because your waves, as opposed to exiting the plasma and hitting your detector here, get cut off and get reflected by density regions above the critical density inside the plasma. So we'll talk about accessibility. Yeah, I think those are good reasons. Yeah.
Do we do anything with the higher harmonics? Or
In this course, I'm no longer talking about the higher harmonics because it gets quite complicated. If you go to Hutchinson, you can apparently find out things about like high energy electrons in the tail of your distribution from the high harmonics. And in general, your emissivity contains lots of information about the distribution function, unless you end up in this optically thick regime. And so if you look at the shape of the high harmonic lines, you might be able to say something clever about the electron distribution function. So if you want to study like runaway electrons or something like that, you can do that. But I had to cut something out of the course, and that's what I cut out here. But yeah, go to Hutchinson's book if you want to. Yeah. Other questions? Anything online? I'm so quiet I can hear the cryopump compressor. Okay, good. Well, actually, yeah, the only thing I will say here is that this signal will not, of course, be nice and smooth. It'll be very noisy. And the point is that in general, noise limits your measurements of delta TE over TE. These are the temperature fluctuations. And the reason why you might be very interested in measuring temperature fluctuations is because, as we discussed, I think, a little bit ago with reflectometry, if you have fluctuations in density and temperature driven by turbulence, that will cause anomalous transport of particles and heat out of your plasma and limit its efficiency as a fusion reactor. So an ongoing problem is how to measure these density fluctuations, temperature fluctuations, so that we can understand turbulence better. And so one thing we'll now talk about is correlation electron cyclotron emission, and that is a technique which is specifically designed to measure very small temperature fluctuations inside the top. Is that what I'm going to talk, or am I going to talk about accessibility? I'm going to talk about accessibility. Have all that run up. I completely lost it. Right.
What is the noise in that case from? I'm used to thinking of like thermal noise as being the source of that. It's like you're looking at it being thermal
Well,
noise. Again,
obviously, there's fluctuations in the temperature, which will produce a different intensity, but there are also thermal fluctuations in the number of photons being produced, right? The sort of shot noise type thing. There's also noise from the fact your detectors are in a noisy environment and they're not perfect and things like that. So yeah, we'll talk a little bit more about the sources of noise when we talk about correlation, electron cyclotron emission, which again, I thought I was going to do now, but it turns out I'm doing accessibility. So we'll get back to that. But yeah, think about just in general, whenever we make a measurement, we're going to have some noise with it. In this case, it just is very difficult to make. These detectors are very difficult to work with, and at 100 gigahertz or so, you tend to have a lot of noise. Yeah. Okay, any other questions? Okay. Okay. So the question of accessibility can be phrased as a question of, can the electron cyclotron emission reach the detector? If it can't, we can't detect it. So all of this beautiful technique is useless. Now, in general, when we're doing something with an MCF device, we're going to be measuring perpendicular to the magnetic field. And that's just a simple geometric constraint that our device, whether it's a stellarator or a tokamak, looks like this, and therefore you'll tend to have magnets that look like this, and so the only gaps are to look in this direction here. You, of course, can design other geometries. I'm just using this as an example here, and because the magnetic field is predominantly the toroidal magnetic field, our angle theta is equal to pi upon 2. So what modes are propagating, what modes is the electromagnetic radiation, the ECE radiation, propagating as inside our plasma? We discussed 4 modes. X mode, and we'll start with the O mode, because it's much easier. The other mode is the empty. So once again, we think about our plasma as a circular cross-section and a magnetic field which falls off as roughly 1 upon r. And so what I'm going to plot is a drawing with the r-axis and the frequency of different modes within the plasma here. And I'll plot this r-axis. I'll have 0. This is going to be r over r0. R0 is the coordinate to the middle of our circular cross-section. And so this is the center of the plasma, 1 here, that's 0, call that 2. The plasma is going to have some boundaries here and here. Very tight aspect ratio, talk about, it's okay. And so for the O mode, we know that the dispersion relationship is just n squared equals 1 over omega p squared upon omega squared, like that. And if we think about a typical tokamak, we know that the density is going to be peaked, right? So we're going to assume that we have a tokamak where we've achieved good particle confinement in the core. We know the density has to go to 0 at the edge anyway, otherwise there wouldn't be the end of the plasma. And so we're going to assume that we've got some density profile that's a little bit like this. And that means that at the edges of the plasma frequency, omega p, is 0. Remember, the plasma frequency goes as Ne squared plus a few other constants. And that means in the middle, it's going to peak. It's going to be the highest plasma frequency. That plasma frequency is important because waves below the plasma frequency are evanescent. So if you have a wave that's propagating in this region of frequency position space, it's going to be evanescent. It won't propagate. It won't reach us. Okay, what about the cyclotron harmonics? Well, they go as magnetic fields, and they also go as 1 upon r. So this is maybe the first harmonic, the second harmonic, the third harmonic. Let me just label these a bit better. Omega, 2 omega, 3 omega, like that. So in the picture that I've drawn right now, if I have a cyclotron frequency here, born at this point near the far edge of the plasma, and I follow the trajectory of that wave outwards, I don't pass through the evanescent region. This wave is going to make it to my detector. Of course, it may also be absorbed, as we talked about, and become black body, but the general idea is that this wave could propagate out without absorption, and certainly the second and third harmonics could all propagate out. But what if my plasma was a little bit denser than this? What if I increased the density in the core a little bit more? Then I could end up in a scenario where there is now an evanescent region. And in fact, almost all of this wave will get reflected back to the high field side, to the R towards 0 side, and only this region will propagate. So this stuff will be reflected, and only this bit. And the stuff that's born inside here can't even be born, right? There's no mode in which for that electromagnetic radiation to be emitted. Okay, so this can still propagate. So that means that for a sufficiently high density, if I draw my tokamak cross-section again, there is a region where omega, capital Omega, is less than omega p, that's this region here, where I will not get electron cyclotron emission from. So this effectively says that high density blocks ECE. And you could imagine the density could even get so high it blocks the second harmonic or something like that. So this is a challenge if you're designing a tokamak and you want to have some magnetic field and some density. And obviously those are not free parameters because we have data limits and things like that. But if you're designing some tokamak, you might end up in a situation where you don't have accessibility to this first harmonic, and so you can't use it as a diagnostic like you wanted to.
Just to ask again,
Yeah.
what happens when it's emitted under the plasma frequency?
I think it can be emitted. There's no mode for it to go into.
So if you zoom in close enough, right, we're not collisional, so you still have orbiting electrons, and we're saying that the far field would get destroyed by the plasma effects, or I guess
would
or would it get reflected back, right? Like
get reflected too.
It's a good question. For those online, the question is, what actually happens to the electric fields generated by gyrating particles in like a single particle picture in this region? What happens if you try and launch a wave evanescently? Well, you were telling me the other day that if you're launching your waves from too far away from the plasma, they evanescently decay until they couple into the plasma where there is a mode that they can fulfill. So what happens to the energy that is lost So some of the energy is coupled into the plasma. What happens to the rest of the energy from when you do like low field side launch? Is it reflected back into the antenna?
I think, well, I think it's, lost in a scrape off layer to some extent, but
Okay.
reflections also.
Well, so you're saying it's collisionless, but maybe this is one of those places where a small collisionality comes to the rescue and saves us, right? So there's lots of cases where if it's collisionless physics breaks, that probably means that something happens such that the collisionality becomes high enough to save the day again. What am I thinking of specifically? Backless sheets, actually, where you have you say my sheet is collisionless, and then you violate all sorts of fundamental laws of physics, and then you're like, well, perhaps it's slightly collisional, but not enough that I care about it, but just enough to save the day. So I don't know. That's a great question. I'll have a think about it. I'm probably not going to find the solution to it, but if anyone else does, feel free to put along the answer or something like that.
But radiation does need to be emitted at least, right? Because it's still a moving charge.
Right. So the question is what does the particle lose energy? Does it just decide not to emit because it's moving? Yeah, I don't know. I suspect there are also some limitations to the WKB picture that we're using here and things like that. So I don't know the answer yet.
I have an even more evil question.
Okay, go for it.
Does
I
that
see.
influence the process that generates the harmonic components?
Oh yeah, that would be good, wouldn't it? Yeah. No, so guess I don't know the answer to that one either, but that's a great question. Yeah, cool. Nicola?
So we maybe look at it from the way we looked last class and when you enter the evanescent region, it says starts falling and the point is you never get oscillation. You still get energy release via the wave, but it's not a wave, it's just an exponential decay.
I don't think you do get energy released by the wave. The point of the evanescent wave is that energy that you've lost gets reflected back. It's not absorbed inside the plasma, that's for sure. And that's true whether it's a plasma or a block of wax with some microwaves, right? So that's just a property of whether the waves can propagate or not. But I don't think the energy gets dissipated in the medium.
And that's what's spooky about when you have.
Yes, that's what's spooky about having a gap that the wave just sort of goes through and then appears out the other side. Yeah. I mean, so in this case here, you could imagine if you had a small enough evanescent region. Oh, that's interesting. Okay, if you have a small enough evanescent region, you could have some radiation that couples to the other side where there's a mode it can propagate into. Similarly, if you have an evanescent length scale which is long enough, then the plasma inside this region could couple to some modes outside, right, and evanescently produce radiation. I will say this is much more complicated than what Hutchinson has in his notes, and I am not an ECE person. These are great questions. I'm going to keep going before someone asks another question. I've almost run out of tea as well. That's how stressful this is. Good. Right, let's do the X mode. So the X mode has n squared equals 1 minus, you really shouldn't write this down, we've talked about it loads before, I just want to write it on the board so that we are staring at it a little bit. Okay. And just to remind you, with this simple O mode example, this surface is when n equals 0, and so this is the cutoff. So the question, and it's pretty obvious that the cutoff in this case is when omega equals omega p squared. What's much less obvious for the X mode is where the cutoffs are, right? So this is a complicated formula. We can go rearrange it and find out what we get out here. And what we find out is that we have cutoffs for a wave frequency omega less than omega L, and I'll explain that to the left resonance, and also for a wave frequency that is between what's called the upper hybrid and the right resonance as well. And I haven't defined any of those. I will do that in a moment. But just to say there are now actually two regions in which we have cutoffs. Previously, we just had this region with a cutoff for omega less than omega p. Okay, so you can go to Chen and you can go look up all of these, and you find that the upper hybrid is the combination of, well, upper hybrid squared is equal to the electron gyrotron frequency squared plus the plasma frequency squared. That's why it's called a hybrid frequency. It's like a sum of two other important plasma frequencies. And then these left and right cutoffs, which are right in one go, with left over right, meaning there's going to be plus and minus signs. And for the left wave, you take the top sign, and for the right wave, you take the bottom sign. This is equal to a half minus plus omega plus omega squared plus 4 omega p squared to 1/2. So looking at that, you think, oh, someone's had to solve a quadratic. And indeed, that's what happened. Okay. Doesn't necessarily mean very much to you at the moment, apart from that these, I'm just going to move this 2 down a little bit so it's closer to a symbol it's actually meant to be referring to. It's clear that we have a complicated set of different cutoffs here. So what I'm going to do is draw again this diagram. R upon R0, frequency of the mode inside the plasma, 1, 0, 2, and we'll do the edges of the plasma here and here. Now it turns out that the lower cutoff here is going to look very similar to this O mode cutoff. And the reason is that if we go to a region where NE at the edge is equal to 0, then omega p is equal to 0, and we have minus gyrotron frequency plus gyrotron frequency. Oh, that's 0. Okay. And then we can also stare at this a little bit and go, okay, it's going to peak in the center. So this is the lower evanescent region down here. So far, so good. And again, we can draw on the same one over R falling modes. For this cyclotron emission. Now, what's very interesting is when we go and ask ourselves, well, where is this second region here? This is the region bounded by the upper hybrid and omega R. Well, let's do the same thing. Let's ask ourselves at the edge of the plasma, where the density is 0 and the plasma frequency is 0, the frequency of the upper hybrid is just going to be the frequency of the first harmonic here. And actually, conveniently, the frequency of the lower hybrid is also going to be the frequency of the lower harmonic. And we can play the same game at the other side, here and here. And if you stare at these for a little while, you'll realize that the upper harmonic is always slightly higher than, sorry, the upper hybrid is always slightly higher than the first harmonic. And the right-hand resonance is even slightly higher than that. So this is the right-hand frequency, and this is the upper hybrid. Pause, let me write something like that. It's all based on some excellent notes that Hutchinson made for 22.611, which is still floating around amongst the grad students. If you can get hold of them, these are very nice diagrams. They are in some form in the textbook, but the ones in his notes are better. So, anyway. What does this mean for accessibility?
You need a minimum of the second exponent harmonic.
Yeah, if we're going to observe from the high field side, sorry, the low field side, out at large R, which is where we tend to put our detectors, there's no way this wave is going to get through this evanescent region, evanescent coupling notwithstanding, right? Because if we emit here and it's got to travel in this direction up, it's hit the region. If we emit here, it's going to travel up, it's hit the region. So we have got a complete cutoff in the center here. And if I left myself slightly more space, I would draw that. I'll draw it directly underneath this one. So now, I again have my tokamak cross section like this, and I effectively have an evanescent region looks a little bit like a banana. Right in the middle here. This is the upper hybrid. And this is the right-hand resonance. So if I have any emission anywhere at the fundamental, that's capital omega, it's going to reflect back. Say it.
So what?
I don't know. I thought you were going to tell me I should put my detector on the high field side.
I was going to, but not. Is this helpful in the sense of like, because you now have no first harmonic cyclotron emission, you can like very confidently do your black body thing?
Well, no, you can't, because it's that emission which becomes black body.
Okay.
If that's blocked out, you can't see it at all.
Okay.
Basically, what it's saying is, so there is a black body spectrum at some frequency. The plasma should be emitting here at some frequency with that black body spectrum, but that frequency gets blocked. It cannot get through the evanescent region.
Sure.
So we can't see any of the radiation from this side on the far side. We can only see radiation from here.
So yeah, high field side sounds like a great idea.
High field side is a good idea for this. Yeah, exactly. Now, I didn't go into this at all, and it seems slightly obscure, the exact place where it crops up in Hutchinson, but it turns out we had this conversation before about like whether you have O mode or X mode. And of course, it's not at all clear to us like which of these two modes the gyrating particle couples into, right? There's no reason, we haven't done nearly enough mathematics to know that. It turns out that predominantly ECE is in the X mode. By like a factor of 10 or something like that.
That's extremely unfortunate.
It's extremely unfortunate for us. And yet, we soldier on. So, yeah. If you have high enough density, this region, of course, could go like that. Block out your second mode as well. Completely possible. So, it depends an awful lot on the density of your talking about, or whatever system you do. All right. I wanted to get onto correlation ECE, but I don't think we're going to. I don't really want to start and not finish. Questions? Yeah.
Do we have a general rule or intuition for the second harmonic intensity in terms of like if we can completely block, you know, the fundamental frequency, if we go up to try to detect the second harmonic frequency, would that be possible practically, or is it just kind of too low?
No. So it's definitely possible. If you look in Hutchinson's book with his example spectra, you will see a spectrum with second harmonics in, and they're very clear. The trouble is they may be optically thick, which may be good. So that might be fine. Like you'd be happy if they're optically thick because you will see some emission from them. So it just is complicated as a short answer, right? So they should be detectable, but they may have been attenuated by the optical thickness. They may have been blocked off because our density is too high, and so there's an evanescent region. So yeah, there's lots of things you need to do the calculations for your plasma to work out whether you're going to see them or not. Yeah. Any questions online? Okay, I think we will leave it. Oh yeah, go on.
So I guess is there, why is it that the upper hybrid and
The left and right resonances, yeah.
yeah, why do they have to meet the cyclotron frequency?
Yeah, absolutely. It's a great question. It's not completely obvious. The upper hybrid one, imagine we're at the edge of the plasma here. So this is the plasma edge. And at this point, any at the edge is equal to 0, which means that our plasma frequency at the edge is equal to 0.
Okay, yeah.
And so then if you stare at this for long enough, you get the idea. Cool. But yeah, it did. When I first saw this picture, I'm like, wait, that's too much of a coincidence. Is it always like that? And the answer is yes, it is always like that. There's no combination of density and magnetic field you can come up with where that's not true, which is kind of cool. Okay, I think we're good for today then. If anyone does have any questions, they can come up and ask them. See you on Tuesday.